Hey guys, what's going on? I am recording this primarily for my Wednesday section because we did miss class last night. I had COVID last week, and then yesterday my fiance, who also had COVID with me, was sent to the ER with chest pains. He is home now, and he's doing all right. And so that's why I missed class. And that's why, if I seem a little not myself today or a little frazzled, that would be why. Um, he is home and he is doing well right now. Um, so anything I say about specific dates is going to be targeted towards this Wednesday section, although I will share this with both classes. So this homework should have been due right before our Wednesday class, and this one should be due next week. Be cautious, even though it's only two questions, it is a little more, say, I don't know, meaty. There's more to it. There's a lot of parts to it. There's a lot of work to it. So don't let the two questions confuse you or trick you into thinking it's a short assignment. We were supposed to have our first test on week 4. When you see test and quiz, just kind of interchange them. I think most in writing it says quiz. I tend to say test. Anyway, it was supposed to be next week. I don't think that's fair. I don't think that's fair. So we're going to push it back a week. So instead of so class was on the 1st. I'm recording on the 2nd. The test was supposed to be on the 8th, but let's make it on the 15th instead, because I think we deserve an in-person review before that first test. Okay. Most important thing, we talked about week 1. The foundations were huge week 1, but the biggest new material, I'll say, is the law of cosines and the law of sines. That is going to be 1 point on your test. It's either actually 1 or 2 points on your test, 1 or 2 questions on your test out of 3. So it is definitely a priority. The law of cosine says that the resultant force, or your longest force, is equal to the two component forces squared added together. The squared of the resultant equals component 1 squared plus component 2 squared minus 2 times the magnitude of the first component, the magnitude of the second component, times cosine beta, or B, where B is the angle opposite the resultant force. We can switch these around. So if you wanted to, let's say we wanted to say Q squared equals P squared plus R squared minus 2PR cosine A, we could do that. We would just have to use the angle that's opposite whatever is set outside of the equation, right? Or on the other side of the equal sign. Most of the time in this class, we see it with the R squared cosine beta, but just know that you can change it around. Our law of sines is a proportion. It basically says that the magnitude of our side lengths is going to change proportionally with the sine of its opposite angle. So in this case, let's look at sine of A. So sine of angle A, opposite that is Q. So either sine A over Q equals beta in this case was opposite R. Not super clear in this drawing, but beta was opposite R, so that would be here. And the last one is just the final ones, vector P and its opposite angle. Obviously, if it's proportion, we could have sine on top in the numerator and magnitude in the denominator, or we could do reverse, as long as we're consistent with every single term. So if I did Q over sine A equals R over sine B equals P over sine C, it's the same thing, right? Last week, we introduced the XY component method, and in doing that, we also introduced unit vectors, our main Cartesian unit vectors, and we're going to go into other unit vectors today. But the Cartesian unit vectors, if you were to move along the x-axis, we consider that the I vector, and if you were to move along the y-axis, we consider that the j vector. You may have seen it in some calculus classes or other classes, but that's one thing we started introducing last week. We also talked about breaking up a force into its x and y components. That's essentially what the xy component method is to break a force up into its components, so you can add those components and you'll know how your resultant force behaves along the x direction and along the y direction, and then eventually you can get your resultant force, all of your resultant forces behaviors. Magnitude of the resultant force is going to be the square root of the sum of the squares, so that's square root of the x component squared plus the y component squared. And the one that I caution the most on this slide is tangent theta. Be cautious, you're always going to get an angle between 0 and 90 when you're using this. So just be cautious that you adjust that angle so that it makes sense with your problem. That probably will make more sense as we go into example problems. This week is all about adding a third dimension. Our third dimension unit vector is k, so our k is along our z-axis. So we're starting with particle physics in 3D. It's going to be similar process to our 2D problems. It's just about getting our brains to kind of wrap around that spatial element. If there's a cable, a chain, anything like that, a rope, the tension is going to go, or the force is going to go exactly in line with that physical element. So use your physical geometry to find force directions if needed. We'll talk about how to do that. Create the free body diagrams, identify important equations, solve, and check your work. So this is where actually, let's go back one. So a force vector is equal to its x component in the I direction, y component in the j direction, and z component in the k direction. So what that means, maybe let's try to think of a different way to describe it. So I, j, and k are unit vectors describing our Cartesian coordinate axis. They have a magnitude of 1, which means that all they tell us is directional information. I tells us 100% in the x direction, j tells us 100% in the y direction, and k tells us 100% in the z direction. But when we're working with more complex forces, let's find an example problem. A force like this, it's not that straightforward. Let me just pause one moment. Actually, let me finish my thought and then I'm going to pause. It's not that straightforward because our forces are going to be going in complex directions. So each vector has its own unit vector. Its unit vector is a magnitude of 1, and it tells you the direction that force or that vector is going. So it just gives you directional information. So if we have a full force vector that is going in some combination of x, y, and z direction, we can separate out its unit vector. One way to do that, and I would say this slide kind of is more so, in my mind, where are our unit vectors coming from? What do they mean? So to get the y-axis, the y element, you're going to use this equation. Theta y is the angle from the y-axis to your vector. What that's going to do is you can also separate out, using that same theta y, a vector called FH. What FH is a projection of that force on the xz plane. So if you were to stand on top of a box, and if this were a cube and you were to stand on top and look down, what you're going to see, you're not going to see the y-axis, right? You're just going to see the x and the z-axis, and you're going to see the projection of F onto the xz axis. That's what FH is. If you were to squish it all down to one plane, that's what FH is. Once we have FH, we can then separate it into its x and z components using phi, which is the angle from the x-axis to FH. The amount of times that we have theta y and phi is really uncommon. Like, think about a problem. Realistically, you're going to have a position of two different points rather than like theta y and phi, right? It doesn't happen like that in the in the real world. I used to hate when people said that because school is still the real world. But when you're working with physical problems, you don't often get these types of measurements or metrics. Now is when I'm going to pause. Okay, I'll be right back. So a force or a vector, so a force is a vector. A vector is a combination of its magnitude, its amount of greatness, its size, and its direction. Magnitude we can separate out. Direction is our unit vector. So if you multiplied the magnitude by the unit vector, you would get the full vector altogether. When we're looking for magnitudes in three-dimensional problems, we still have to do the sum of the squares. So the square root of fx squared plus fy squared, we have an extra term here, right? We have our z's now, so we'll add in our z squared as well. Okay. That's called the direction cosines method. Our unit vector is just this element, but like I said, that's not how we're going to get it most often. Do know though that it's always, unless you have like one term with a 1 and two terms with a 0, so 1i, 0j, 0k, 0i, 0j, 1k, something like that. Unless you have a situation like that, every single term is going to be a decimal because your unit vector needs to have a magnitude of 1, which means the square root of the sum of the squares needs to equal 1. So they're all going to be decimals. Okay. The way that we do that in this class, or the way that we do that more often, I think there is one or two homework problems with the cosine method, direction cosine method. But finding a vector from 2 points is really what we're going to do more often. And I'm telling you, this slide looks a little more confusing than it is. Let's say we have, what can I draw on here? Let's say we have m is 1, 2, 3, and n is -2, 5, and 1. Okay, those are our 2 points. So we know, so let's say there's a rope. I can't change slides now that I drew on it, I don't think. Let's say there was a rope and it connected these 2 points. We know that our force is going to go along that direction. Depending on where you cut it, it could either go from M to N or from N to M. So you're going to have to gauge the sense or the positive negative type of direction based on the problem. But let's just say in this case, M minus N. Sometimes, depending on how the problem is phrased, if it's like find the tension in this rope, there would be 2 answers that would be correct, and they would just be in opposite directions. Okay, they would be equal but opposite vectors. Okay, so what this is saying is the D vector is the vector that joins M and N. It's made up of the X element in the I direction and so on. The X element just means x2 minus x1. So if we're doing n minus m, -2 minus 1, our dx would be -3. Our dy is y2 minus y1, so y2 is 5, minus y1 is 2, so that's a +3. And then our dz would be z2 minus z1, so that would be 1 minus 3, so that's a -2 there. This line right here is just saying that a force vector equals a force magnitude times its direction, its unit vector, which is its direction. Okay. D here is the magnitude of your D vector. So the magnitude of your D vector is going to be the square root of the sum of the squares. So the square root of -3 squared plus 3 squared plus 2 squared, -2 squared, right? So then if we were to divide each of these terms by this, let me do that for a minute and pull up a little Excel sheet. Okay, so we said we have, so I want to do the square root of 3 squared plus 3 squared plus 2 squared. You know what? Just because squareds can be a pain. That's what I'm going to do. So Wolfram Alpha is like a calculator that, I don't know, it's just a more advanced calculator, programmed, I guess. So I'm just doing this to get our final magnitude. Right? And so our magnitude in this case, there's an extra number in there for some reason. So our answer is the square root of 58. So if we go back to this, okay, we have all of these. So now our vector here would be negative 3i plus 3j minus 2k. To get our unit vector, we'd have to divide each term by the square root of 52. So it would be negative 3 over the square root of 52 times I, plus 3 over the square root of 52 times j, plus 2, negative 2, minus 2 over the square root of 52 times k. So you see that all of those would be decimals. Once we have that, if we were to have the magnitude of f, we could multiply this unit vector by the magnitude of f to find the f vector. If we had the f vector, we could divide the f vector by the unit vector and get the magnitude of f. Okay. Where is, how do I clear the, oh, perfect. Let's go back one. Okay, so know that if the cosines method here works, the direction cosine methods here works, and our finding the distance between 2 points to find a unit vector method, the terms would be equal. How important is this slide? I'm not sure. I don't think it's the most important thing. Okay, so in this case, the tension in the guy wire is 2,500 newtons. Determine the components Fx, Fy, and Fz of the force acting on the bolt at A. Okay, so the first thing I would do in this problem is determine the location of each of these points. So for point B, I'm saying that this is our y-axis, this is our x-axis, and this is our z-axis. So B is at 0x, 80y, and 0z, and A is at 40x, 0y, and negative 30z. Some of the problems, the geometry can be a little hard to see. So if that's ever a case, ask me what the dimensions are. But in this case, so then we're going to subtract either A minus B or B minus A. This is one of those questions where, because it's saying the tension is 2,500, it could be, so if we were to analyze point B, the tension would be going downwards in this direction. If we were to analyze point A, the tension would be going upwards in this direction. So whether you ended up with this unit vector here or a positive 0.424, negative 0.848, and negative 0.318, either one would be acceptable. I hope that makes sense. But first step, we're going to subtract the points. So in this case, they did point B minus point A. So negative 40, positive 80, and positive 30. The magnitude is the square root of the sum of the squares, which comes out to 94 in this case. So the unit vector is going to be each of these terms divided by the magnitude. That's going to come up with a unit vector that's going to be made up of decimals. If we wanted to check the correctness of this, we could do a square root of the sum of the squares of this, and everything should equal 1. Don't think it's the best use of time, but just trying to get that point in that a unit vector is a magnitude of 1. It will not affect your brightness information. Okay, so now to get from our unit vector to our force vector, we're going to multiply that force magnitude they gave us in the problem statement by the unit vector we have, and then we're going to get our force vector with its what is specifically happening on the x-axis, the y-axis, and the z-axis. Second part of this question was to get the angles. So we can use our cosines to do that. Like I said, this element is more my priority. If you understand the cosines, that's a bonus. But this is my first priority. Okay, I think I am going to stop there. Like I said, the test is going to be pushed back a little bit, just so that we can talk in person about it all. Okay. Let me know if you have any questions. I know that was a really quick one. Before I leave, actually, let me go to your homeworks. To the two, actually, it might be here still already. Homework 2. Okay, so for this first question, the first question on your homework is still in 2D. The pulley is held in position. If the pulley is held in position, this means that we're in equilibrium. The summation of forces should equal 0. Summation of forces x, y equals 0. And if z, if we had it. Okay, so there are 2 cables. One is CAD. So CAD goes from the center of this pulley around A down to D, and there's a force P acting at D. It doesn't explicitly say it in this problem, but there is no friction in this course until our very last week. So there's no friction in these pulleys. We won't even talk about pulley friction, honestly. We'll talk about belt friction and just friction in general. But there's no friction loss here, which means that all throughout this rope, we're going to have the force of P and Q, right? I'm sorry, P, and then Q is on the other one. The other one, so my point is there's going to be consistent force within consistent tension everywhere between C and D along that one line. And then our other line goes from A around this pulley to B. That is going to have its own tension value consistent throughout, because this pulley is not going to lose any. This pulley doesn't have any impact from loss of friction either. Okay. The other thing to note is that these 2 lines are going to be parallel. So if this one's at 55 degrees, this one is also at 55 degrees. Okay. And the second question is the one that is a little bit more, is our 3D question. Forces at P and Q are applied. This problem drives me nuts, because why even add a force of Q if Q equals 0? But I guess just to be tricky, I don't know. Find the value for P for which the tension in cable AD is 305. Okay, so the way I would approach this question is with our unit vectors and separating it into XY component method. So when you have a drawing that is so when we're working with unit vectors, it doesn't matter if we're working in meters or millimeters, because once we get to that unit vector, it's unitless. It doesn't matter. When we divide by the square root of the sum of the squares, we're getting rid of any unit that was in there. And so if you feel more comfortable working in millimeters, do that. If you feel more comfortable working in meters, do that. This is our origin point. So A would be at 960 millimeters X, and 240 millimeters Y, 0Z. B and C are both along the Z axis, so they are going to have Z values, Z elements, but no X or Y element. This D is at 0x, positive 960y, and negative 220z. Okay. And the other thing to note is that obviously this is an equilibrium case. It doesn't say it, but it is equilibrium, and that's how we are able to solve it. Okay. Now, let me know if you have any questions, and I will talk to you all soon. And like I said, I promise we will get back on track. And I'll see you all on Wednesday.